Hi everyone, welcome to our next ocean series. This is between WHOI and the Nature Tech Collective. Happy November. It would be great if some of you turn on your cameras, we can see who's here, maybe some of you from the collective are here. Yeah, we're going to get started really soon. For the moment, we're going to let people trickle in. For all of you to know, we are recording this session, so if you're wondering if people can't make it or if you need to drop off early, we'll have that recording and we can send it to you afterwards. And I'll go ahead and introduce the Nature Tech Collective. So I'm Zara. I help run the NTC community at the Nature Tech Collective. We are an alliance of 180 organizations that are committed to accelerating a nature positive future. And the way we help our members is we amplify their work, we connect them with one another, and we create sector intelligence and reports about different aspects of nature tech. We've come out with a number of sector maps and reports this year, and at some point you'll hear about them. But one of the things that we do is we have sub-communities around specific topics within the nature tech space, and ocean is such a crucial one of those. So I'm so thankful for Amal for leading our ocean sub-community and this webinar. And I will let you, Amal, take the stage.
Thank you so much, Sarah. Hi, everyone. Good morning, good afternoon, good evening, wherever you're joining us from today. Welcome. So my name is Amal Katata. I'm founder of New Finance Startup, and I'm also a member of the Nature Tech Collective. I coordinate a series of webinars and workshops focused on ocean tech. Today, I would like to take a few seconds before kicking off this webinar to remind you all this is Coral Bleaching Awareness Month. Corals are a very important ecosystem. They cover less than 1% of the ocean floor, but support 25% of life underwater. And today, they're facing an existential crisis. And the threats are so many, all interconnected. There are climate-related threats, mainly ocean warming and ocean acidification, but also human-led threats, unsustainable fishing practices, touristic development, and also diseases, invasive species. But the main issue is really climate change. If we stop climate change, the corals will recover by themselves despite all the threats that they're faced with. And so to in regards to climate change, in the last webinars and this one and the upcoming ones, we're focusing on marine carbon dioxide removal approaches. Why? Because the ocean is our superhero when it comes to fighting climate change. We won't get to net zero without both mitigation and adaptation efforts, and some have to be in the ocean, which represents 71% of the planet's surface. But what if we could amplify the capacity of the ocean to store carbon? In the last webinar, we invited Dr. Wilbert from Planetary to talk about ocean alkalinity enhancement. And today we have the honor to be joined by Dr. Ken Buesseler from Woods Hole Oceanographic Institution. So Dr. Ken Buesseler is a marine radiochemist who studies the fate and distribution of radioactive elements in the ocean. Their radioactive decay properties can tell us something about timescales or how quickly processes take place. Applications include studies of the ocean carbon cycle, where the naturally occurring isotopes of thorium tell us how quickly and how much carbon is carried on sinking particles from the sunlit surface ocean through the ocean twilight zone to the deep sea. His lab has also been active in response to radioactivity released from disasters, such as the impact of radioactivity released from Fukushima Daiichi nuclear plant, and from earlier sources such as Chernobyl or atomic weapons testing at the Marshall Islands. So impressive. Before we kick off our webinar, just wanted to give you an idea of how we will proceed, we'll first have presentation by Dr. Ken, and we'll leave Q&A towards the end. If you have any questions, please feel free to drop them in the chat or raise your hand, and we'll address them after Ken's presentation. Also, I'll remind you to this webinar is going to be recorded. Everyone who registered on Luma will receive a notification when the recording is available, and you can rewatch it, share it with other people. So thank you so much for joining us today. Thank you, Ken, for being with us. Please take it away.
Thank you. I'll bring up my slides here. Make it full screen. All right. So yeah, it's my pleasure to be here, Amal. Thank you, and those listening today. There's an earlier date on this, but we've modified it for today to give you some idea about my work. I'm a senior scientist at the Woods Hole Oceanographic Institution. I'm also director of a nonprofit called Exploring Ocean Iron Solutions. So we're going to look at ocean iron today and its ability to potentially remove carbon dioxide as part of a marine carbon dioxide removal approach. You know, like you in this audience, I think from what I've heard and what I know of you, we're deeply worried about climate change. You just have to look at the news to see the suffering, the heat waves, the wildfires, the crop losses, the sea level rise, the damage we're seeing to the ocean with acidity, loss of sea ice. So I think we're all coming from the same place. I happen to have spent close to 40 years, actually more than 40 years as a marine scientist, and I care about the ocean on this planet. And so I want to advance our understanding of the ocean's role in climate. So that's really my motivation. Part of that, this Exploring Ocean Iron Solutions group, I formed that group about 3 years ago now, after we completed a study through the academies in the US about the ocean's role and how could it specifically take up more carbon dioxide than it does now. I've worked in this area of ocean iron solutions and ocean iron geochemistry in my past research on the biological carbon pump. So I think I kind of know what the research needs are in this area. So that's been my focus, though it's not the only focus and the only way to do this, as you will hear during this talk. So I like to start with introductory slides that you've probably already seen, right? Everybody looks at curves like this. We're looking at emissions of CO2 on the vertical axis here. I put this up just for the scaling of gigatons, billions of tons of CO2 emissions. We're somewhere near 40. That orange dashed line, we don't know how that's going to go, but it continues to increase. What we do know, the dark gray, is we have ways to reduce those emissions. That's the first thing we should all be doing. I know people here on this call come from different parts of the world. Some countries are doing better than mine, but we have ways to switch to non-fossil fuel energy sources. Maybe not bring that to zero, but that's a path we all should be supporting, getting behind. But I think we've learned, as we look at future predictions, we've already essentially messed up the concentration of greenhouse gases, particularly carbon dioxide in the atmosphere. We're going to have to remove some of that. That's the blue color below zero here, called negative emissions, or CDR, comes from that carbon dioxide removal. And so we're looking at trying to reduce the majority of the 40 billion tons we emit, but also start to take up, learn how to, we really don't know how to do this, maybe 10 billion tons per year of carbon dioxide. So to me, it's a somewhat optimistic slide, even though these numbers, that orange curve is discerning, but we do have ways we could do this if we so choose, and if we learn how to do that blue part, the carbon dioxide removal part. So that's what this talk will be about. The other thing though I want to put in front of you is, billion ton, gigaton. Some people use petagrams. What is that? It's an astoundingly large amount of carbon that we emit every year in the form largely of carbon dioxide. Humans throughout history have emitted about 400 of those units. With land use changes, it's actually close to double that. But if we use this 400 gigatons of carbon, if we just want to say, what's 1 billion tons? how big would that look like? So I have this train car image, I think it's from Australia, and a train carrying coal. If you thought, well, how long would that train be to carry just 1 billion of these tons? What's the magnitude in terms of something we can see? Well, if there were a train track around the equator of this planet, it would circle that equator 4 times to carry 1 billion tons, a gigaton. So these scales are truly astronomical, what we're doing and what we have to come to grips with. But so we need basically planetary solutions to deal with this type of emission. So at the bottom there, we're going to talk about the ocean now. So where does all that carbon go? And one of the numbers here that's much bigger than 1 gigaton or 400 is the deep ocean. So this is the storage capacity. It's not how much goes in and out every year. But if you look at that ocean circle, this very large number, 38,000 billion tons, gigatons, that's by far the largest active reservoir that cycles carbon dioxide that would be entering the atmosphere. The atmosphere is close to 900 in these units. That's about 50 times smaller. That's where we don't want the excess greenhouse gases. You've probably heard about land-based CDR, whether it's planting trees or direct air capture. That's about 15, 20 times smaller than the ocean reservoir. And we have competing uses on land for some of these areas. So it's hard to see, I use this slide to say basically there's no solution to our climate crisis and carbon removal without considering the ocean. It's where it's going to end up already, and the oceans already take up about 1/3 of our greenhouse gas emissions. But it's big relative to all of human emissions. So that's something we have to consider. I guess I'll point out, I think I have time, but that blue carbon, the thing that many people experience, mangroves, salt marshes, seagrasses along the coastline, are important and highly productive areas that store carbon naturally, but they're just not that big. It'd be hard to put all of our emissions, say, in coastal settings. We have to look to the ocean in its larger scale for carbon uptake to make a difference here. So for iron, I'm really going to go pretty quickly, but realize that the ocean is full of microscopic plants called phytoplankton. Just like plants on land, and again, apologize if this is all very familiar to you, but most people don't appreciate that these plants in the ocean, the microscopic ones, that image on the left is a chain of diatoms, produce about half of the oxygen on this planet. So they're very important in terms of their photosynthesis, right? The uptake of carbon dioxide, production of oxygen occurs equally in the ocean as it does on land. What people don't realize, I didn't appreciate till early in my career, is that to grow plants, you need sunlight, you need nutrients, you need typically warm enough temperature, but they also need small amounts of iron. And this is an essential nutrient, just like nitrogen and phosphorus, for growth. They don't need very much, but we started experimenting in the open ocean back in the 90s, early 2000s there, where if we add a very small amount of iron, in the case on the right, it's an image from a satellite. So we're going from the microscopic to a global image looking down 60 degrees south in the Southern Ocean. You can put in a very small amount of iron, in this case, 1 ton, and get something like 4,000 tons of carbon dioxide in terms of the growth of those plants, their organic material, and then they're lost, they're sinking. So there's a huge ratio there that's an advantage, is inherent to this approach over other marine CDR approaches, is a little iron kind of goes a long way. So we show that. I was part of some of those experiments, but we kind of left it there. We weren't really thinking back then about using this deliberately. Some companies were getting set up, but I think most of the public at the time, and I was certainly part of a group thinking, well, we can reduce emissions and get our way out of this. I think we've long passed that point. So we have to think about, well, where does that carbon go? Because if it just grows but doesn't get deep in the ocean, it really won't have any effect on that atmospheric carbon dioxide. And so the first of 2 slides to introduce that concept is, I just love this quote. Rachel Carson was a brilliant marine biologist and environmentalist, and she wrote several books but she calls this marine snow. If you look out from the submersible, or if you go scuba diving or even skin diving, most of what you see are those little flecks of things. Certainly in New England, where I live, the ocean here is not pristine blue and clear. It's full of a lot of particles. That's organic matter largely. And that organic matter we call marine snow. She called this the most stupendous snowfall on Earth because constantly, wherever you look in the ocean at the different depths, we have this carbon-rich material that comes from the surface, that horseshoe, that green chlorophyll patch. A lot of that material sinks down into the ocean interior. So what does that mean in the case of iron? And this is something we didn't capture in our studies 20, 30 years ago. It's this question: how much of that carbon, if you put iron in at the top, you create the green biomass, the plants that grow, the phytoplankton, they die or they're eaten or they run out of essential nutrients, they sink and they carry that marine snow with them as part of what we term the biological carbon pump. I'm sure some of you have heard that term. I think what's often not appreciated, one thing is as particles sink, they're the food supply for the midwaters and the deep, dark oceans. So a lot of that carbon gets remineralized, we call it, converted back to dissolved forms that never reach the deep layers, but a lot of it does. And the important thing is that scale on the right is once you get out of that surface sunlit zone, you can be sequestered or removed for timescales of centuries. This is now below depths typically of 500 meters or more, and millennia if you get into the deep waters. I think it's underappreciated. We don't have to bury this carbon. We just have to get it deep enough, we think, to impact climate on human scales of centuries to millennia. That's really what a lot of the techniques, whether using seaweed to get carbon deep, or in this case, phytoplankton stimulated by iron, we're not talking about sequestration and burial. It's just getting it deep enough to matter for climate. And that's important. And that's the key question that we don't know. And so we're proposing through, and I'll give you some examples of studies to get at that additionality and durability, if you've heard those terms. How much additional carbon could we move down and how durable would it be? So I mentioned durability, and I'll just show you a map. I think we have a pretty good idea of those layers. We know a bit about ocean circulation. There are a lot of really very smart physical oceanographers who can tell you, okay, if you map out the ocean and you put in color here the depth to which you have to reach that sinking marine snow to be sequestered or durably removed from atmospheric contact for 100 years or more, that's depths here, often in blue, 500 to 1,000 meters. It varies, we know that, but this is pretty well known. And so I think we can reach a point with measurements and studies to get at that, what we often call a centennial ton. It's not just enough to say, I'm going to remove a ton of carbon. It's how long will that stay sequestered? It's a bit like growing trees, right? Versus soil sequestration. There's different timescales. So kind of as a recap, because I want to really kind of go through some other issues too, is why is it worth considering? Well, we know from models in nature that we could probably get 1 or 2, even more gigatons of CO2 per year if we just consider areas that are low in iron and high in other nutrients. And I really haven't, I guess, said this today, but the main form of iron naturally is dust. And so we're often looking for areas far from those continents and the high seas where dust input is low, iron is low, and that's what limits their growth, not the regular nitrogen, phosphorus, high nutrients. This 1 to 1,000 ratio is super efficient compared to anything else in marine carbon dioxide removal. Nature does 1 to 100,000. So I say that's inefficient because Mother Nature does a better job. Because of that efficiency, it's relatively cheap. Iron's a very abundant mineral. It would not take scaling up a lot of additional mining, less than 1% changes to get to gigaton scales. And we've done this over 13 times back in the 90s and early 2000s. Now, I don't want to say there's no risk, there's no things we need to care about. Certainly, before you would ever deploy iron at scale, and our group is looking at studies to see should we do this or not, or when or where, we have to think about the changes as particles sink in oxygen below them. There's some very good papers about that. It tends to be relatively small, easy to measure. And certainly at the pilot study scale, they're very insignificant changes to oxygen. Downstream impacts, there's this word nutrient robbing, right? It's really a redistribution. If you take up nutrients in one place, you're not having as many nutrients downstream. Well, I'll give you some examples and some real numbers. Not sure again how much you are up on the literature, but those numbers I feel are small relative to the impacts of removing carbon dioxide removal. HABs, you may have heard of harmful algal blooms. That was in the news 20 years ago. And people said, well, Ken, some of those diatoms, those microscopic plants, are the similar class to produce coastal harmful algal blooms. Pseudonychia is one of them, producing domoic acid. We've measured for that. It has never been seen to be higher in those field studies, but we'll continue to look for that. We'll continue to look for other greenhouse gases. As you remove carbon and sink, you can produce things like nitrous oxide and methane. So you don't want to offset the CO2 removal by producing greenhouse gases. And we've done that. We've measured that. We'll continue to measure that. Typically, it's 10%. So I'm going to step back a little bit from iron and just talk about different ways to do this. And you heard about one, I guess it was the ocean alkalinity enhancement. It's called mineral addition on here. Microalgae fertilization is ocean iron. Like direct air capture, we can use electrical energy to split apart and remove CO2 from the ocean. We can grow seaweed and sink those types of products to the deep ocean. We can upwell waters to make nutrients. We can directly inject it. But I think this section of the talk is really all of these will have impacts. We know more or less about them, but they all have impacts. And there's been several studies. I mentioned the National Academy studies I was on. This is more recent, 2025. International authors, I want to attribute this to some hard work by lots of people, but we've started to look at them. And there's broadly methods on the left that enhance this biological carbon pump. Iron in the green bar is the green box is what we're talking about mostly today. And they all have durability. They can be tens of years to thousands of years. The energy demand differs. Some of these, like electrochemical, it takes a lot of energy, direct air capture in the same way, to make those processes happen, to extract the carbon and then store it somewhere. So until we reduce our use of fossil fuels, I think it's good to know those pathways, but I think it's impractical. It's a lot easier to stop emissions, use anything that's fossil fuel free to power electricity rather than CDR. And technical readiness, because we're pretty far along, we kind of know what we're doing with iron. We could do that tomorrow. Now we have to be concerned about marine ecosystems. I kind of disagree with this circle. If you remove CO2 from the atmosphere, that's the only way we're going to reduce ocean acidification, this idea the ocean's getting more acid. So that has to happen. And we don't really have many use conflicts, I think, to worry about. So the really bottom line is, and I'll reemphasize this twice, but just be aware. You can look at all of these different ones and there'll be fans of one or the other on this call maybe, but they all have to cause change. Otherwise, they're not working. And then if we don't do anything, the half full, half empty glass, we are experiencing these ocean elevated temperatures. Oops, didn't mean to go that fast, but ocean acidification, I've said these things. The ocean's becoming deoxygenated. There's ocean heat waves. There's consequences on land. So doing nothing, to me, is not a choice, or it is a choice, but we should not follow that path. So just two specific examples, just to give you some nerdy numbers, if you want to go back. A paper in 2025, Andreas Oschli's, ocean iron fertilization in that model. Now we can't do this on these scales, but over 100 years can get rid of close to 200 billion tons of CO2. That's a big number. It's 1 or 2 per year. And we were talking about trying to get to 5 to 10. Yes, this changes subsurface oxygen 3%. There's a change in the area that's considered suboxic, particularly off South America, but you have to weigh that change versus removing 200 billion tons. Alessandro Tagliabue and others, a little bit earlier, a paper a couple of years ago, they did a separate model. They saw 150 tons removed in a slightly shorter 70-year period of 2100. they show a decrease in oxygen that's even smaller and a biomass decrease off South America. So nutrients become harder to deliver to the surface ocean if we warm the ocean. That number is 15%. If we don't do anything, it became 20% when they looked at what happens because of this nutrient redistribution. Well, again, a 5% change in biomass predicted 70 years from now has to be weighed against removing 150 billion tons of CO2. So I just want to emphasize all of these are going to have issues. All of those predictions rely on models, and in this case, the biological carbon pump. And so Stephanie Henson and others predicted in 2022, well, let's look at those models. How well do they predict this carbon flux billion tons per year that's happening already? This isn't a CDR model. This is coupled climate models. Numbers there range from 5 to 12. So already, if you're kind of following these numbers, that's a big variability, right? Just in the best models they could find in 2022 for the ocean biological carbon pump. And so just to put that in words, oops, I'm not a modeler. You know, they're basically saying we don't do a very good job, both with the current number, 5 to 12, and to the extent that those numbers are going to go down in the absence of any interventions. Most of them tend to go down. I mentioned that we stratify this ocean, we make it less productive, which results in less carbon coming out of the surface. But there are a lot of processes that are just not in these models that allow you to make predictions, which is why I'm such a strong advocate for field work to inform these models. I think another example I want to get onto and back to, which has come up more recently, was this oxygen. And what about deoxygenation? We're really going to mess up the ocean. Well, okay, again, there's a lot going on in this single figure, and I'll summarize it in words, but basically, here's another model prediction. Ocean depth, 0, 100 to 400 meters. So as plants grow, this is time on the right, 180 days out, about a half a year. The lighter at the top is where there's sunlight. You produce more oxygen if you were to add iron. This is a very specific example in the Northeast Pacific. You also decrease or change oxygen below as you break down that sinking marine snow. That number is quite small based on predictions, based on observations 13 times. It is something to worry about, but when the headlines come out and you see images of dead fish on a beach, that will not happen due to pilot studies. I don't think it'll happen on a global scale. And I think this is an older quote from Andy Watson, Phil Boyd and others, atmospheric scientists with them, but we need observations to make those models as accurate as possible. So I think that's the point of these two slides. We have models, they're imperfect, need to get to observations. So this is just another way to say that with a pretty picture of a research vessel from where I work. I've spent close to 2 years of my life on ships like this. We've got to get out, we've got to put out observation systems. We've got to, in this case, do experiments larger and longer, adding iron to see what the consequences are, not just at the surface, but also below those iron patches. So what does that kind of look like? Well, a lot of what we do in exploring ocean iron solutions is work with modelers and observationalists who've done these kinds of experiments. We can do things like here, I guess I should point to the map on the right side, planning the next generation of a field trial. What would that look like? Yes, we did these 20 years ago. We didn't get at that sinking flux. So we're looking at a place here off Alaska and Canada that's limited by iron. We know that from past study. It's near a time series site. I don't know how many have heard of Ocean Station Papa, probably not too many, but in oceanography, Canadians, US have been going there for almost 50 years now. We're proposing to go there because those colors indicate nutrients, nitrogen, nitrate. It's quite high, but it's low in iron. So the left is just a loop of a model that runs out about 3 months. It's part of a publication we have. The top left is you add iron here. We've just added iron here in, I think it was May, now it's getting to June. ocean currents carry that iron around. They produce more phytoplankton below it. Those panels are basically mirror images of each other with some differences. You see the change in nutrients. We don't take up all of the nitrate. We don't want to do that, but we do want carbon to sink. And we call that carbon export. And that lines up pretty well with the phytoplankton, the iron. This is a prediction down at that centennial ton depth of 500 meters. So we can make those predictions. We don't have to know the units, but we do have a good way to organize and come up with hypotheses and field trials that we think are necessary. Another thing to know, no matter which model we use, we've tried several, they all have kind of these same impacts. You add iron, phytoplankton respond, nutrients like nitrate get taken up, carbon that's formed starts to sink, and this goes away over time. So it's not as if they produce vastly different results or we create a legacy impact in that region for all time. It's winter mixing comes along, you reset those numbers. So experiments, even on this scale, which is about 10 times bigger than what's been done before, do not have permanent impacts. Oceanography's come a long way, though, in those 20, 30 years, and this is just a very simple cartoon, just with lots of things on it. Again, for those who know ocean technology, we now put out gliders that can move passively in the ocean and can do studies for months, measuring ocean properties, temperature, chlorophyll, oxygen. We can put in floats. There's something called the Argo floats. There's thousands of these in the ocean. We can move up and down and track. What the idea on this picture is, there's an area in the middle, 30 by 30 kilometers, where we add in iron. There's areas outside that we observe, and so we compare inside and outside. Traps are generically a word for something that captures that marine snow. Things can move up and down on wires, skim along the surface, and yes, we will bring out ships like the ones I told you, the picture I showed that I've been on. But more and more we can put autonomous surface and underwater vehicles to monitor those impacts. So people like me don't have to go out and we can monitor for timescales that's many months rather than a few weeks, many weeks. Getting near the end here, I just want to introduce ExOIS, we lovingly call this. This is this international group launched in 2022. The EX is important. We're exploring ocean iron solutions. We do not have a solution. I think you have to watch out when people come up and say, we have a way. Often that's more of a commercial approach. We have 60 plus people who meet pretty regularly, at least 37 institutions, 9 countries, and we're housed where I work, Woods Hole Oceanographic Institution, but we're independent, and we seek and write papers on what the scientific priority should be. We speak to public audiences, and we try and look for public and private partners. We do not accept or use commercial funding for carbon credits as a way to fund this. We want to separate the funding for credits from the independent research that we think is so essential to advance the science, so society, political groups can decide what to do at what scales. I think this is my second to last slide. In 2022, the very first thing we did is we set out, we were scientists, we know how to do that, we think. I mean, it's not perfect, but we also think that codes of conduct are important, how you move forward. And again, ocean iron fertilization has a history of some, call them the rogue geoengineers or the geoengineer pirates that just go out and do things. We think that's not the way forward. We really have to follow international permitting processes. We're doing this for the benefit of humans and environment. Otherwise, why do it? We're not doing it for profit, in other words. We have to have clear lines of responsibility that relates to permitting. We are, as scientists, open to publishing our research, doing risk assessments, iterative independent assessments when we go out. Once we reach funding to do that, anyone can come and join us. We want to engage the public in this. And again, importantly, we're not seeking carbon credits as we do that. So my final slide, leaving this for questions. You know, all marine CDR, every talk you hear, just make sure you realize it will have impacts on the ocean. Otherwise, there's no point. These can change things we call geochemistry, that would include oxygen, change the ecology, whether you change alkalinity, iron, grow seaweed, all will hopefully decrease atmospheric carbon dioxide. I think for any marine CDR approach, the science is incomplete to predict those impacts at scale. Yes, make predictions, but be aware, all models are wrong, some are useful. That was an economist, George Box, who said that decades ago. They're lacking in this case in those key biological carbon pump processes that would allow you to predict effects locally and downstream, and just the magnitude, that plot I showed. I firmly believe a group that field studies are needed. It's not the only thing. We're doing modeling, we're doing outreach, we're looking at new technology, but the impacts of moving into the field are generally small and temporary, at least for ocean iron fertilization. We're nowhere near those billion-ton scales. We got to 1,000 tons with 1 ton of iron. Maybe we can get to 10,000. We've really got to keep that up so that in the next 5 to 10 years, we figure out how to do this. During that 5 to 10 year period, we need to promote fossil fuel reductions. There's nothing here. It's not either or, it's and. We have to keep saying that. We have to consider multiple ways. I don't think this is the only type of marine CDR we should be considering, or even not considering land-based, but they all have impacts. And I think it's time to work together. Often what the press likes to cover, what people focus on, is the differences, and mine is better, mine's bigger, or something, mine's cheaper. I think we just don't know those things. So ExOIS kind of actively trying to support each other. Why CDR? Why the oceans? Why iron could be one of those solutions. That's my elevator talk at COP30, where I'll be starting this weekend to make the case. So with that, I think I'm just going to stop showing slides, maybe, so I can see people when we take questions. I can bring them back up if we need to. Thank you.
Thank you so much. This has been super insightful. I've shared some links for the references you mentioned as you were speaking. We have a question from JV Poe, Planet Ocean. I'm gonna unmute you. Oh, okay.
Hi, Amal. Hi, Ken. Thanks so much for the presentation and the slides. I really appreciate the pragmatic approach you guys are taking, and the obviously evidence-based and science-driven approach to looking into these kinds of solutions. For context, Planet Ocean is a VC looking into ocean-based solutions to climate change. And so, of course, we're very interested in the space of MCDR. I joined this call hoping to understand more about the impact side of things, because as we explore potential investments into this space, obviously one of the biggest obstacles is the expected pushback around what many cite as the lack of evidence or the lack of data on the impacts on ocean ecosystems and marine ecosystems of many of these solutions. So when you cited, for example, no observed harm, I was keen to learn more, and if not during this call, I'd be happy to do further reading into what no observed harm means. But I also worry that the organizations like yours and mine versus the organizations that are raising these red flags are drawing lines in different places. So rather than my first question, I'd like to focus on the second one, which is how have you historically navigated those conversations with more conservative institutions and entities in terms of, defining what is considered risky, what is considered harmful, or when solutions can be deemed safe enough to start seeing deployment at scale?
Right. No, excellent points. And, I hope I said when we talked about harm, those are the field trials. 13 times we've done this. We know what happens when Mother Nature puts in iron. A volcanic eruption is one example. And so those are temporary perturbations. They disappear. You can go back the next year. You do not see changes. We try to measure everything we know that could go wrong, the risks like harmful algal blooms. We look for those toxins. They didn't show up in past experiments. What I find kind of really the point is that the field trials, if we don't have more information about those impacts below the surface, as just one example, through longer studies, it's very hard in those models. I try to emphasize how different they are to make a prediction, oxygen, downstream effects. And so I would say let's move ahead on the models. Let's do that under international protocols. I didn't mention if you work out in the high seas where there's low dust, you need to follow something under the London Convention, London protocols, which would be an environmental impact assessment. You can't just go out. You could, I guess, but we won't put iron in the ocean in the high seas without a permit. In the US, that involves Environmental Protection Agency. So we're in the process of writing those permits to get out to the high seas under that regulation. And that makes you identify what the risks are, convince not just the EPA, but the public who have comment period that the benefit can outweigh the risks. But we're the first to say we shouldn't be out there deploying this. We're also trying to, I'd be curious your opinion, venture capital, it seems easy. There's a lot of money flowing around if it's tied to carbon credits, but we're hoping we can find more visionary groups to think that, well, look, we can step back for 5 years, 10 years, whatever it's going to take to do the studies without having an incentive tied to a carbon credit. We'll measure those numbers. We'll tell the world if we got 1,000 tons or 10,000 tons or 100,000 tons removed or zero. But if we get financially rewarded for a bigger number, I think that's an inherent bias, conflict of interest that we're trying to avoid by staying out of the voluntary carbon markets, which is primarily where some of the venture capital money is coming through. So, we're trying to distance ourselves from the profit motive at this stage, develop protocols. We will pass those on. We'll tell the world what they are. We'll publish that data. And then companies can come in and commercialize following those protocols. And if there are markets, potentially sell those voluntarily or to countries that use us to meet their obligations. Does that help a bit? But it's a challenge, right? Hands off the ocean is very common, but that half empty, half full glass is a bit of the attempt to say, we've already disrupted the planet and the ocean, and what studies can we do to do something about it?
And I think you put it best when you said the approach of doing nothing is possibly the worst approach we could take because we see where we're headed with that trajectory. Thank you, Ken.
Thank you.
I'm scanning for other questions, but in the meantime, what is the expected timeline, Ken, for reaching that conclusion of whether to proceed and to kind of offer that technology in the hands of commercial developers? What is your view on the potential timeline?
Because some of these experiments are say take a year to get permitted and then a year to go out, we're thinking 5 to 10 years is what ExOIS has a phase 1 for 5 and a phase 2 for 10 years, because you will try this, say, in the Northeast Pacific. We'll go back out to do a replication. Maybe we'll change the conditions, time of year, but then we'll move around to other locations. The Pacific upwelling region has low iron and enough nutrients. There are areas of low nutrients, by the way. That's kind of a new thought among our group and others, that you could stimulate what's called nitrogen fixation. There's certain plankton that take nitrogen out of the atmosphere. They don't need it pre-existing as a dissolved nitrate nutrient. So nitrogen fixation is worth looking at. And then the Southern Ocean, a large amount of we call them excess nutrients, areas with high nitrate and phosphate and others are centered around the ice-covered Antarctic continent, because that's where with covered land and ice, you don't get a lot of dust, right? So there are areas where we've done studies before. So we would look at all of them, and then you start making choices, right? Where do you get the most bang for your buck? Where is it logistically just too hard to work? Where do we want to stay away from marine protected areas because we don't want to change that? So hopefully, but that's definitely this 5 to 10 year time frame. And then to the last question too is like, that's what I'm worried about, this rapid commercialization, that it seems like an eternity for a company. Most business models don't allow you to spend 10 years figuring something out, but that's kind of, I think, what we need to really have enough confidence to make some of these choices.
Thank you, Ken. Pass it on to Alberto. Good to see you here.
Yeah, thank you. Thanks, Amal. Ken, thank you very much for the insightful talk. I was in grad school when Victor Smetacek was pioneering some of the early iron fertilization experiments, and I remember kind of dismay of his group when they ran some early deployment in the Southern Ocean, and they realized they were not getting the export they were expecting to see. Has something fundamentally changed in the understanding of iron fertilization, or is it a matter of location, or what's the current view on that?
Yeah, important question. And Victor, by the way, in their last experiment, they did see deep export in the Southern Ocean. So
Okay.
the problem has been, we go out for 30 days and it takes weeks for those plants to grow. Part of showing you that plot, that animation, it can take a couple of weeks to get the response. So if you're out there for 3 or 4 weeks and you're leaving the area, most of the groups kept adding iron to get a bigger and bigger chlorophyll response. We never were at a point where we could measure the complete demise, the return back to normal conditions of those patches. So we designed experiments successfully to look at the production, the iron limitation side, but not the carbon loss side. That really wasn't studied. I happened to work on that myself, and I would be annoyed. We got out there 30, I think we exceeded 30 days once on the experiments I was on, and just started to see that sinking flux, that loss of carbon. The horseshoe I showed was only about 6 weeks after. You know, you really have to stay out and do it. And the other thing is technology has improved. So we know from natural systems that I've studied my whole career that there's always going to be some carbon sinking, whether it's 10% or 50% that gets down to these durable layers. It's harder to predict. The good thing about iron in that sense, those efficiencies, diatoms, that microscopic view was a chain-forming ketocerous diatom that has silica associated with those plants. That tends to be one of the more efficient ways to get things quickly to the bottom. Because what happens when you sink slowly, you get eaten along the way, and then you don't become durably stored. You just get back into the atmosphere when the water mixes in the wintertime. So the types of phytoplankton that grow, the food webs, tend to be in nature ones that sequester more carbon.
Mm-hmm.
But even if we know it's 10%, you could find that that might still be useful, given that it doesn't take much iron to make a difference. So I get 500 tons per 1 ton added instead of 1,000. I think the number is going to be more like 10,000 if we even get closer to nature. But that's also be wary of those costs. People say, well, it's $100 a ton or $1,000 a ton. In our case, that's the big variable. You can change that number by a factor of 5 pretty readily with these different models, and make a prediction that would affect the cost directly by a factor of 5, right? So I think there's a lot to be learned on that export side that we just weren't able to do 20, 30 years ago.
Yeah. Thank you very much. Thanks for the